Welcome back to the deep dive. So, when we look at the life cycle of consumer electronics today, specifically those massive high-density lithium-ion battery packs that sit at the end of their usable life, the standard industrial approach has, well, it's basically always been about mitigation.
Right, yeah. Damage control, essentially.
Exactly. We look at these degraded, chemically exhausted packs, and we see a severe hazard. Like the baseline assumption for decades has been that we are dealing with a toxic liability.
Absolutely. And best case scenario in that traditional model, we run them through pyrometallurgy or hydrometallurgy.
Right, which takes a massive amount of energy.
Oh, an unbelievable amount. Just to claw back a tiny fraction of the cobalt or lithium, really just to slow down the rate at which we're filling up landfills.
Yeah, it's basically just delaying the inevitable.
It is entirely a strategy of delayed disposal because traditional recycling models are inherently linear. I mean, we extract the raw ore, we process it, we use it until the chemical entropy becomes just, well, too great. And then we downcycle whatever we can salvage. The structural and chemical integrity of the materials is basically assumed to be permanently compromised by the time it reaches that end-of-life stage.
But the stack of engineering white papers and the technical schematics we are diving into today completely shatters that linear assumption.
It really does. It flips it on its head.
Yeah, we are looking at the JSUN Halbach 1 ecosystem today. And the premise here is just a radical inversion of material science.
The central thesis is wild.
It is. The idea that a completely dead, degraded lithium-ion battery isn't a toxic liability at all. It is literally the highly refined, perfect, raw feedstock required to build an autonomous, levitating supercar.
Which just sounds like pure science fiction.
It totally does. So, okay, let's unpack this for everyone listening.
Yeah.
Today, our mission is to trace the entire architecture of this closed-loop system. We're starting from the physical recovery of that hazardous waste, moving right through the cold plasma chemistry that alters its atomic structure, and going all the way to the maglev highway infrastructure that actually powers the vehicle.
Yeah, and that transition going from literally shredding waste to advanced material synthesis is where this gets highly, highly technical.
Right. Because to understand how they accomplish this, we have to look at the exact nature of the feedstock first, right? Like, how are they breaking these batteries down?
Well, they aren't just melting down the batteries into a homogeneous slag, which is what pyrometallurgy does. That's the typical approach.
Right, just throwing it in a furnace.
Exactly. Instead, they are physically shredding them and then painstakingly isolating the shredded electrodes to extract very specific atomic components.
Okay, so what exactly are they pulling out?
Primarily, they want the disorganized carbon from the anodes and the metallic nanoparticles, mostly nickel and manganese from the cathode matrix.
Which fundamentally sidesteps the global mining apparatus entirely.
Completely.
I mean, by sourcing the carbon and the heavy metals directly from the existing e-waste stream, they are establishing a completely circular upcycling process. They aren't digging for new lithium. They aren't digging for new graphite.
No, the need for new mining is eliminated.
And just looking at the thermodynamics of traditional extraction, I mean, the energy savings here must be astronomical before we even get to the synthesis phase.
Oh, they are. Because we already spent the megawatt hours pulling these elements out of the earth and refining them, decades ago.
Right, the work is already done.
Precisely. The embodied energy of those materials is retained. So we are bypassing the ecologically devastating, highly water-intensive, and frankly, geopolitically fragile supply chains associated with virgin ore extraction.
Yeah, the JSUN process basically treats the urban e-waste footprint as a high-concentration, above-ground mine.
That's a great way to put it. But the key differentiator here is that they aren't just recovering the carbon to use as, a low-grade filler for something else.
Right, they are chemically reorganizing it.
Yes, into a lattice that vastly outperforms its original state.
It's crazy. It's like, okay, think about it like this. It's like unbaking a burnt cake just to extract the flour, and then somehow using that flour to forge a diamond.
That is exactly what is happening at the atomic level.
Okay, so we have the shredded, separated electrode materials. We have an abundance of disorganized carbon, plus these residual nickel and manganese nanoparticles.
Right.
The challenge is restructuring them, which brings us to the absolute core of the JSUN technology, the plasma-catalytic chamber.
This is where the magic happens.
Seriously. The sources detail the use of standard industrial microwave generators for this. And they're operating at 2.45 gigahertz, pushing anywhere from 800 to 1200 watts per chamber.
Right, and they pump that energy into an argon and hydrogen gas environment.
So why 2.45 gigahertz? Is that number significant?
It is critical because that frequency is a standard, highly reliable industrial, scientific, and medical radio band.
Wait, isn't that the same frequency my kitchen microwave uses?
It is exactly the same frequency magnetrons in standard home appliances use.
Wow. Okay, so it's already a mass-produced technology.
Precisely, which means the hardware is already highly commercialized and totally scalable.
So they take these industrial microwaves, and when that energy is injected into the argon and hydrogen gas mixture, what actually happens?
Well, it excites the gas. It strips the electrons away from the atoms, creating what we call a non-thermal or cold plasma.
Okay, I really want to analyze the physics of this non-thermal plasma, because as I was reading the documentation, the thermal delta here, the difference in temperature, is what makes the whole system viable.
It's the linchpin of the whole process.
Because the specs state that the electron temperatures inside this plasma spike to roughly 10,000 Kelvin.
Right. Very, very hot.
But the bulk gas, temperature-like, the actual macroscopic thermal environment of the chamber that you can measure with the thermometer, remains between just 300 and 500 Kelvin.
Which is basically just a warm room up to maybe a hot oven.
Yeah. I'm trying to square those two numbers. If we are driving an electromagnetic field hard enough to accelerate electrons to 10,000 Kelvin, how does the system prevent the plasma sheath from transferring all that kinetic energy to the heavier ions? Like, why doesn't it just instantly incendiate the carbon feedstock?
It's a great question. And it comes down to the vast difference in mass between the electrons and the heavy particles, combined with the specific collision dynamics of the microwave field.
Okay, break that down for me.
So an electron is roughly 1,800 times lighter than a single proton.
Right.
The high-frequency oscillating electric field of the microwaves couples extremely efficiently with those low-mass electrons. It accelerates them to massive kinetic energies.
And that's your 10,000 Kelvin equivalent.
Exactly. But when these hyper-accelerated tiny electrons collide with the much heavier argon atoms or the hydrogen molecules or the carbon feedstock itself, the energy transfer is highly elastic.
Oh, I see. It's a momentum transfer problem.
Yes.
Because the mass disparity is so huge, the electron just bounces off without actually depositing significant thermal kinetic energy into the heavier nucleus.
Exactly. It's like throwing a ping pong ball at a bowling ball at 1,000 miles an hour.
The bowling ball isn't really going to move.
Right. The heavy ions and the neutral gas molecules barely heat up, which is why the bulk temperature stays around that 300 to 500 Kelvin mark.
That is fascinating.
It really is, because if this were a thermal plasma, like an arc discharge, where everything is in thermal equilibrium.
Like a welding torch or something.
Yeah, exactly. If it was like that, the carbon would just instantly oxidize. It would thermally degrade into completely useless amorphous ash.
So, by maintaining this strict temperature decoupling, the cold plasma protects the physical integrity of the feedstock, but it simultaneously weaponizes the electrons.
Weaponizes them is the perfect phrase.
So they are weaponizing them to break the existing molecular bonds. The high-energy electrons are colliding with the argon and hydrogen, initiating this huge cascade of ionization and creating highly reactive radicals.
Yes, specifically the hydrogen radicals. They seem to act as the chemical scalpels in this process.
Chemical scalpels. I like that. So they bombard the degraded carbon feedstock and basically just cleave the tough carbon bonds.
Yeah, but the radical bombardment is highly selective, which is the brilliant part.
Selective how?
The hydrogen radicals effectively etch away the sp3 hybridized carbon.
The sp3 bonds, those are the disorganized amorphous bonds, right?
Exactly, the messy degraded stuff. But it leaves the stronger sp2 bonds relatively intact.
Okay, so we are chemically dismantling the degraded battery structure without relying on brute force thermal destruction.
Right. We aren't just burning it down. We end up with an active, highly energetic cloud of carbon atoms that are perfectly primed and ready to be rearranged.
Which leads directly into what the papers call the chemical choreography.
Yes.
Because having a plasma chamber full of active carbon atoms is only the first step. They naturally want to agglomerate into useless soot, right, just to minimize their surface energy.
Right. Carbon atoms are sticky. Left to their own devices, they just clump together into soot.
So they need a guide.
Yeah.
And this is where the retained heavy metals from the battery waste re-enter the equation.
This is such an elegant part of the system.
It is. The nickel and manganese nanoparticles aren't just useless byproducts that they couldn't filter out. They are actually the fundamental kinetic drivers of the graphene growth.
They function as the nucleation sites.
Okay, tell me more about how that works compared to normal methods.
Well, in a traditional chemical vapor deposition or CVD process, you rely on a pristine copper or nickel substrate, like a flat sheet of pure metal.
Right, which you have to buy and prepare.
Exactly. But here, the nickel and manganese nanoparticles from the dead battery act as a dispersed three-dimensional catalyst matrix floating right within the plasma.
Wow.
So the active carbon atoms naturally absorb onto the surface of these metallic nanoparticles.
And looking at the activation energy required for this phase transformation, the math highlights a massive thermodynamic shift.
It's a huge drop.
Yeah, standard graphene formation requires an activation energy of approximately 350 kilojoules per mole.
Which is an enormous energetic barrier.
Right, which is why producing it usually requires extreme heat or insane pressure. But the introduction of these specific D-block transition metals lowers that activation energy down to just 120 kilojoules per mole.
It is nearly a two-thirds reduction.
So how are the nickel and manganese actually achieving that reduction at the atomic level?
Yeah.
Like physically, what is happening?
It's all about electron orbital overlap. The d orbitals of those transition metals interact perfectly with the p orbitals of the incoming carbon atoms.
Okay.
And this interaction stabilizes the transition state of the carbon-carbon bond formation.
So instead of forcing the carbon atoms to, like, overcome a massive repulsive energy barrier just to link together,
Yeah.
the metallic surface essentially provides a lower energy pathway.
Exactly. The carbon atoms dissolve slightly into the metal surface or migrate across it, and they link arms in a perfectly ordered hexagonal sp2 lattice.
And the sources emphasize that the catalyst specifically stabilizes the edges of the growing lattice too.
Yes, what's fascinating here is how crucial that edge stabilization is.
Because graphene islands naturally have high-energy, unstable edges, right? Either zigzag or armchair configurations.
Right, and those unstable edges are highly prone to curling in on themselves or binding with random impurities in the chamber.
Which totally ruins the structural integrity and just creates multi-layer amorphous clumps again.
Exactly. But the nickel and manganese effectively pin those edges down. They physically enforce a defect-free monolayer growth.
So that edge stabilization is what ensures the material actually qualifies as true high-purity graphene rather than just becoming cheap industrial graphite powder.
Yes. And by lowering the activation energy so drastically, that entire kinetic process can occur rapidly, even at the relatively low bulk temperatures of the cold plasma.
Which yields a profound implication for the life cycle of these materials. I mean, we are taking carbon that has undergone thousands of electrochemical charge and discharge cycles.
Carbon that is completely exhausted.
Right. Physically fractured, chemically exhausted inside a battery. And through this plasma-catalytic mechanism, we strip it down and reassemble it into a perfect crystalline structure.
We are functionally resetting the atomic clock of the material.
That's a great way to say it. The material isn't just recycled. It is granted a 50 to 100 year functional lifespan as an aerospace-grade structural component.
Because the atoms themselves do not degrade, only their arrangement does.
Wow.
By imposing perfect structural order on disorganized waste, you establish a true circular economy. The materials can be infinitely upcycled without any loss in performance.
Okay, but that theoretical infinite upcycling only matters if the economics and the scalability actually make sense in the real world.
That's the real test.
Which brings us to the industrial realities of this process. Historically, graphene has been known as this miracle material that is basically trapped in the laboratory because of mass production bottlenecks.
It's notoriously hard to scale.
Yeah, traditional commercial high-purity graphene runs anywhere from, what, $50 to $200 per kilogram?
Depending on the supplier, yeah. Sometimes even more.
But the JSUN process targets a production cost of under $12 per kilogram.
And to contextualize that massive cost reduction, we really have to look at the energy consumption per kilogram.
Right, because traditional synthesis methods are just brutal on the power grid.
Brutal is an understatement. Flash joule heating requires instantaneous, massive electrical currents to blast the feedstock.
And CVD, the chemical vapor deposition we talked about, requires highly controlled thermal environments and ultra-pure precursor gases, like high-grade methane.
Right, and those traditional methods typically demand 35 to 50 kilowatt hours of energy just to yield a single kilogram of graphene.
While the JSUN plasma-catalytic method demands only about 14 kilowatt hours per kilogram.
It's less than a third of the energy requirement.
We are looking at less than a third. And when you combine that slashed energy footprint with a feedstock that is entirely sourced from zero cost or honestly even negative cost to waste, the financial modeling behind that $12 target becomes very clear.
it becomes highly profitable very quickly. Furthermore, the operational footprint is remarkably condensed.
Yeah, tell me about the production lines.
Well, we aren't looking at massive, bespoke chemical plants covering hundreds of acres. The architecture is based on modular production lines.
Okay, modular meaning you could just stack them up.
Exactly. A single module is scaled to process 50,000 end-of-life battery packs annually.
50,000 packs. And the yield from those 50,000 packs is roughly 750 tons of high-purity, defect-free monolayer graphene.
Yes.
Let's do the math on that throughput. To process 50,000 packs a year, assuming standard operating uptime, you are running continuous high-volume material handling.
Non-stop.
And 750 tons of a material that is literally one atom thick. I mean, that is an almost incomprehensible surface area.
It's millions of square meters.
The schematics note that this 750-ton yield is sufficient to build the structural components for 10,000 new vehicles per year per module.
10,000 cars from one modular line.
Which entirely localizes automotive manufacturing.
It completely decentralizes the global supply chain. I mean, think about it. Instead of shipping iron ore from one continent to a steel mill on another,
Right.
and then shipping heavy chassis components to an assembly plant across the ocean, you just place these modular plasma-catalytic lines directly adjacent to major urban e-waste processing centers.
So the vehicles are forged from the localized waste of the exact city they will eventually drive in.
Exactly.
It's brilliant. Dot, producing 750 tons of graphene at high speed introduces a critical engineering vulnerability, right? Quality control.
Quality control is the biggest hurdle at this scale.
Right, because if you are churning out all this graphene for vehicular structural components, the atomic lattice has to be flawless.
It has to be perfect.
Because a macroscopic failure in the chassis of a supercar that's being driven at high speeds, that is catastrophic.
Absolutely.
So how does the system guarantee the atomic perfection of the lattice at that immense volume?
Well, human oversight at that scale and speed is physically impossible.
You can't just have a guy with a microscope looking at it.
No, definitely not. Which necessitates the integration of an AI-driven real-time feedback loop.
Okay.
The entire plasma chamber is monitored by an integrated sensor network utilizing high-speed Raman spectroscopy.
Okay, Raman spectroscopy. Let me clarify what that is for the listener. It measures the inelastic scattering of monochromatic light, usually from a laser, right?
Yes, exactly.
So as the laser hits the forming carbon lattice, the molecular vibrations shift the energy of the photons, and that gives us a highly specific structural fingerprint of the material.
Right. It tells us exactly what shape the atoms are taking.
But Raman usually requires a certain amount of integration time to gather a strong enough signal-to-noise ratio. Like, it's not instantaneous?
Usually, yes.
So I'm trying to understand the latency here. What happens the millisecond the AI detects a flaw? How does an AI process scattered light fast enough to adjust a microwave field before an atomic defect propagates into a massive macroscopic flaw?
Well, the trick is that the AI isn't actually attempting to process the entire broad-spectrum Raman signature.
Oh, it's not looking at the whole picture.
No, that would take too much computational power. The edge computing models are trained to isolate and analyze only two highly specific frequency shifts simultaneously.
Which are?
The G-band and the D-band.
The graphitic band and the defect band.
Correct. The G-band represents the in-plane vibrations of the P2 hybridized carbon, so the perfect hexagonal lattice.
That's a good stuff.
Right. And the D-band represents the out-of-plane vibrations caused by P3 bonds, edges, or structural impurities.
Like the laws, the bad stuff.
Exactly. So the system is programmed to constantly calculate the IDIG ratio, comparing the intensity of the defect signal directly to the graphitic signal.
Okay, and the target tolerance is an IDIG ratio of less than 0.05.
Which is exceptionally pure.
Yeah, less than 0.05 is crazy. So if the sensor detects the D-band intensity spiking, meaning amorphous carbon is beginning to form instead of graphene, the AI has to intervene.
In microseconds. Because the AI is only crunching the ratio between those two specific peaks, the computational latency is nearly zero.
That makes sense. It's just comparing two numbers.
Right. So when it detects a ratio drift above 0.05, it dynamically adjusts the chamber parameters immediately.
What exactly does it adjust?
It will instantly modulate the duty cycle of the microwave magnetron to alter the plasma density. Or it will tweak the flow rates of the argon and hydrogen gas to change the radical concentration.
Oh, so it can literally change the chemical mixture on the fly.
Yes, or it will shift the electromagnetic containment to alter the distribution of the nickel and manganese catalysts.
So it's an active closed-loop control system managing chemical kinetics at the atomic level.
Exactly.
It corrects the growth environment dynamically to ensure every single square meter of that 750-ton yield meets aerospace-grade tolerances.
Which is an incredible feat of engineering on its own.
Yeah. Right. Which means we now have an immense volume of structurally perfect, sustainably produced graphene. And this transitions us from the synthesis phase directly into structural engineering.
Now we actually build the car.
Yeah, because the sources indicate this graphene is the primary material for the JSUN Halbach 1's color-active monoshell chassis.
And the monoshell leverages both the mechanical and the electrical properties of the graphene.
Okay, mechanically first.
Mechanically, it is roughly 10 times stronger than advanced high-strength steel while weighing just a tiny fraction of the mass.
Yeah, the total target dry weight for this entire supercar is under 650 kilograms.
Which is insanely light.
That is an absurdly low mass for a high-performance EV. Most modern performance EVs carry a massive weight penalty. I mean, they are often pushing 2,000 to 2,500 kilograms.
Easily.
Just because of the heavy lithium-ion pack and the reinforced steel required to support all that weight.
Right. It's a vicious cycle of adding weight to support more weight.
But dropping the weight to 650 kilograms completely rewrites the vehicle dynamics and the energy requirements for propulsion.
It changes everything. And the electrical integration of the monoshell is just as radical as the weight savings.
Here's where it gets really interesting. The chassis features voltage-regulated iridescence.
Yes. Because the graphene matrix is highly conductive, the engineers have designed the outer shell to function as an electrochromic surface.
Okay, explain what electrochromic means for us.
But passing precise, minute electrical currents through the external layers of the monoshell, the system dynamically alters the refractive index of the material.
Wait, really? So it changes how it reflects light?
Exactly. Its structural color. It is very similar to how a peacock feather manipulates light to create those brilliant blues and greens.
But entirely active and controllable by the driver.
Right. You can literally change the color of the car on the fly.
Which totally eliminates the need for chemical paints, primers, and clear coats.
Yes, which strips out yet another highly toxic, highly energy-intensive step in traditional automotive manufacturing.
That's amazing. But the graphene's conductivity serves a much deeper functional purpose than just looking cool.
Oh, absolutely.
The sources state it is utilized for the structural battery conductors and the motor laminates.
Right. The chassis itself is a functional component of the electrical grid of the car. It's not just dead weight carrying the battery. The body is the conductor.
Wow. And this deep integration of ultra-lightweight recycled materials leads to the ultimate environmental metric of the whole JSUN ecosystem.
This is the number that really matters.
Yeah. We are looking at a process that produces only about 0.05 kilograms of CO₂ equivalent for every kilogram of graphene synthesized.
Primarily due to the incredibly low energy requirements of that non-thermal cold plasma we talked about.
Right. And when you run a full life cycle assessment, so factoring in the complete elimination of raw ore mining, the sequestration of carbon directly from the e-waste stream, the highly efficient 14 kilowatt-hour per kilogram synthesis, and the drastically reduced energy consumption of driving a 650 kilogram vehicle, the math is staggering.
It really is.
The ecosystem achieved net negative life cycle carbon emissions within just 3 years of operation.
3 years. It creates a true carbon deficit.
That's incredible.
If we connect this to the bigger picture, the vehicle effectively removes more carbon burden from the industrial supply chain than is required to actually build and operate it.
So for the remaining 50 to 100 years of the monoshell's functional life, it represents a permanent net negative asset.
Exactly. It is a total paradigm shift away from extraction and mitigation, moving directly into restorative manufacturing.
Okay, so we have an ultra-lightweight, carbon-negative, structurally flawless chassis. But a car is meant to be driven.
True.
And the propulsion system, engineered to move this 650-kilogram monoshell, is where the physics get truly exotic.
This is my favorite part of the design.
Because the vehicle doesn't rely on a centralized motor and a mechanical drivetrain. Instead of a traditional engine, the JSUN Halbach 1 utilizes 4 independent in-wheel motors equipped with double-sided Halbach arrays.
Right. And to really understand the propulsion and levitation mechanics here, We must analyze the magnetic geometry of what a Halbach array actually is.
Walk us through it.
So, in a standard permanent magnet configuration, like a fridge magnet, the magnetic field lines propagate relatively symmetrically from the north and south poles.
Here?
A Halbach array is a spatially optimized arrangement of permanent magnets where the magnetization vector rotates across the sequence of the magnets.
Okay, so it relies on the superposition of magnetic fields. By arranging the magnets so their fields purposefully interfere with one another, you can selectively amplify the magnetic flux on one face of the array while nearly canceling the field entirely on the opposite face.
Exactly. You end up with a localized, hyper-intense magnetic field directed entirely outward from just one side of the array.
So in the context of the JSUN in-wheel motors, these double-sided arrays are oriented so that one face focuses immense magnetic flux laterally into the motor's stator for propulsion,
Right.
while the other face directs massive magnetic flux straight downward, interacting directly with the roadway.
Which means we are dealing with active magnetic levitation.
Maglev.
Yes. The highway infrastructure itself must be embedded with continuous corresponding Halbach arrays.
So when the downward focused flux of the vehicle meets the upward focused flux of the road, it generates a massive repulsive lift force.
Precisely. And the documentation relies on the standard magnetic pressure equation for this.
Let me guess. Lots of math.
A little bit. Basically, the levitation force equals the square of the magnetic flux density multiplied by the effective area, divided by 2 times the permeability of free space.
Okay, that equation actually reveals why the Halbach arrangement is mandatory here, doesn't it?
Yes, it does.
Because the levitation force scales with the square of the magnetic flux density. So by artificially amplifying the flux density on the downward face without adding any additional physical mass to the magnets, the repulsive force is magnified exponentially.
That's it exactly. It generates enough magnetic pressure to completely lift the entire 650-kilogram mass of the vehicle.
Generating a physical levitation gap of 10 to 20 millimeters.
Right. The tires literally do not touch the asphalt.
And the implications for energy efficiency here are massive. I mean, in a conventional vehicle, a significant percentage of the powertrain's total energy output is completely wasted, just overcoming rolling resistance.
Oh, huge amount.
Just the continuous physical deformation of the rubber tires and the friction against the road surface eats up so much power.
But by establishing that 20-millimeter maglev air gap, the JSUN system eliminates approximately 80% of rolling road friction entirely.
80%.
Yeah. The energy required to maintain a cruising speed of, say, 120 kilometers per hour plummets, because the primary resistive force is now purely aerodynamic drag, which the monoshell is obviously already optimized to cut through.
Okay, but wait. This introduces a massive control paradox.
How so?
If we eliminate road friction, we also completely eliminate mechanical grip. I mean, if I am driving a 600-kilowatt supercar and the tires are hovering 20 millimeters above the road, how does the vehicle actually corner? A traditional steering rack relies on the friction between the rubber and the asphalt to generate lateral forces.
Right, the tires have to grip to turn.
So how does this system execute high-speed maneuvers without simply sliding off the magnetic track like a pug on an air hockey table?
It's a great visual, but the control dynamics are entirely managed by the specific topology of those in-wheel motors and the central AI's torque distribution.
Okay.
These are axial flux motors, which differ fundamentally from the standard radial flux motors found in most conventional EVs.
Let's break that difference down. In a standard radial flux motor, the magnetic field travels outward from the center, radially across an air gap, to a cylindrical stator, right?
Exactly. They are highly effective, but they tend to be long and heavy.
But an axial flux motor runs the magnetic flux parallel to the axis of rotation, interacting with a flat, disc-shaped stator.
Right. And that geometric difference is key because it allows the axial flux motor to be shaped like a very thin, highly compact pancake.
Oh, so it fits entirely within the hub of the wheel.
Yes. And because the Halbach arrays are generating such intense flux and the graphene motor laminates are actively spreading thermal loads, these axial flux motors hit a peak efficiency of over 97%.
97% efficiency.
Yeah. They produce massive, massive instantaneous torque.
But the torque is independent. There is no physical axle connecting the left and right wheels.
Exactly. And that independence is how you solve the steering paradox you mentioned.
How so?
The central AI manages adaptive torque vectoring at the millisecond level.
Okay, so when the driver inputs a turn.
The AI doesn't just angle the front wheels. It dynamically distributes highly asymmetric torque commands to each of the 4 independent motors.
Oh, I see. It's actively generating yaw through differential thrust.
Pres-
So, like, if the car is turning left, the AI can apply massive forward torque to the outside right wheels while simultaneously applying regenerative braking drag to the inside left wheels.
Yes. It forces the chassis to pivot directly around its center of mass.
And because it is interacting with the structured magnetic field of the track, the electromagnetic drag and propulsion create a kind of virtual grip.
Exactly. The dynamic simulations demonstrate that this adaptive torque vectoring, which is constantly calculating crosswinds, mass transfer, and the magnetic gap, actually increases high-speed cornering stability and lateral grip by more than 15% compared to conventional tire-dependent EVs.
15% more grip while hovering. That is wild. The system is reacting faster than mechanical suspension ever could.
Way faster.
But okay, let's think about the power draw here. Operating 4 97% efficient 600 kilowatt axial flux motors to maintain levitation, forward propulsion, and constant high-frequency torque vectoring that requires a continuous massive draw of electrical current.
Oh, massive. It's a huge energy demand.
Even with the elimination of rolling friction, a standard lithium-ion battery pack would be rapidly depleted by those demands. Eventually, the battery must run out, right?
Not exactly, which is why the ecosystem incorporates dynamic wireless charging directly into the Maglev infrastructure.
Oh, wow.
The active highway track doesn't just provide repulsive lift, it is a continuous power source.
Okay, so dynamic wireless charging, or DWC. The technical specs here indicate the roadway utilizes resonant inductive coupling to transfer up to 300 kilowatts of power to the moving vehicle.
Right. And it operates at a high frequency of 50 to 100 kilohertz.
Okay, I understand the baseline mechanics of inductive charging. An alternating current in the primary coil embedded in the road generates an oscillating magnetic field, which induces a current in the secondary coil in the car.
Like a wireless phone charger, just on a massive scale.
Right, but I'm looking at the efficiency ratings in the documentation, and I'm highly skeptical.
Why is that?
The documentation claims an energy transfer efficiency of over 93%.
It does.
But in most wireless charging systems, the coupling coefficient just drops off a cliff the moment you introduce a physical air gap.
That is traditionally true, yes.
So how are they pushing 300 kilowatts across a 20-millimeter gap at highway speeds without massive thermal loss and electromagnetic leakage? That just seems impossible.
It would be. Without the Halbach arrays, this raises an important question, and the engineering synergy here is brilliant.
Okay, walk me through the synergy.
The 93% efficiency is achieved through the dual utilization of those arrays. The permanent magnets in the wheel aren't just pushing against the road for lift. The Halbach arrays actively shape and confine the high-frequency oscillating magnetic field generated by the resonant coils in the road.
Oh, wait. So they are acting as a magnetic lens.
Precisely.
Yeah.
They focus the flux lines of the inductive field directly into the receiver coils of the vehicle.
Wow.
It drastically increases the coupling coefficient and prevents the field from scattering into the surrounding environment. So the levitation hardware itself actively solves the air gap inefficiency problem.
So the magnetic arrays lift the car and simultaneously funnel 300 kilowatts of power straight into the solid-state battery matrix.
Exactly.
If we look at the energy balance of the vehicle in motion, the Maglev system has slashed the energy consumption to a mere 0.08 kilowatt hours per kilometer.
Which is incredibly efficient.
But the highway is continuously beaming 300 kilowatts into the receiver, so the vehicle is consuming energy at a vastly lower rate than it is absorbing it.
Which yields the ultimate operational capability of the JSUN ecosystem.
Infinite range.
Infinite range. On equipped highway corridors, the total vehicle range isn't decreasing as you drive, it is actively extending.
That is just mind-blowing.
Depending on the speed and auxiliary power draw, the dynamic wireless charging system adds between 50 and 200 kilometers of total range to the battery for every single hour spent on the Maglev infrastructure.
Wait, really? So you could embark on a cross-country transit, drive at 120 kilometers per hour while hovering 20 millimeters above the road, and exit that highway with more stored energy than when you departed.
Yes. The infrastructure entirely absorbs the energetic burden of long-haul mobility.
That is insane.
And this continuous trickle charging is managed by the AI to remain well within the thermal limits of the battery, minimizing deep discharge cycles and further extending the lifespan of the onboard cells.
So the entire architecture, the graphene synthesis, the monoshell, the maglev propulsion, and the inductive charging, it all operates as a perfectly synchronized loop.
It is a stunning feat of integrated engineering. This isn't just a vehicle, it's the blueprint for a totally closed-loop sustainable ecosystem.
Okay, let's pull all the threads of this narrative journey together for the listener.
Yeah,
Because we have covered so much ground today.
we really have.
We started with literally the darkest element of modern technology, mountains of hazardous, degraded lithium-ion e-waste.
Right.
But instead of burying it in a landfill, the JSUN ecosystem physically shreds it. It separates the carbon and metal nanoparticles and feeds them into a 2.45 gigahertz microwave chamber.
Where the decoupling of electron and bulk gas temperatures in the non-thermal plasma allows hydrogen radicals to cleave the carbon bonds without any thermal degradation.
Right, and those freed carbon atoms interact with the specific orbitals of the retained nickel and manganese catalysts, dropping the activation energy all the way down to 120 kilojoules per mole.
Rapidly forming perfect, AI-monitored, defect-free monolayer graphene at a fraction of the traditional energy cost.
And then, that high-purity graphene is forged into an ultra-lightweight, 650-kilogram, color-active monoshell chassis and highly efficient axial-flux motor laminates.
Establishing a system that operates with a net negative carbon footprint within just 3 years.
Finally, those independent motors utilize double-sided Halbach arrays to lift the vehicle 20 millimeters into the air, eliminating 80% of road friction while simultaneously focusing an inductive field to absorb 300 kilowatts of continuous power from the highway.
Yielding an infinite-range, zero-emission supercar.
It's a complete restructuring of the energy and material economy.
It proves that with precise atomic-level manipulation, there is truly no such thing as permanent waste.
Which leaves us with a massive geopolitical and macroeconomic reality to consider. And I want the listener to mull this over.
It's a huge point.
Because we are currently living in an era defined by the frantic, often highly destructive global race to secure raw materials. Entire economies, trade agreements, and national security policies are built around the extraction of lithium, cobalt, and rare earth elements.
Absolutely. The geopolitical tension is enormous.
But if the JSUN plasma-catalytic closed-loop system reaches global scale, the necessity for that extraction plummets.
The urban centers of the world, which currently generate the highest volumes of localized e-waste, suddenly become the most resource-rich environments on the planet.
Exactly. Think about it. If your dead laptops, your old phones, and your degraded electric vehicles provide the exact, perfect raw material needed to build the next generation of hyper-advanced transportation, the entire supply chain just folds in on itself.
We sever the reliance on ecologically devastating strip mines and fragile international shipping lanes.
The very concept of a resource shortage effectively ceases to exist when we realize that the materials we need are already sitting in our scrapyards just waiting to be reorganized. What happens to the global balance of power when our trash becomes infinitely more valuable than unmined gold?
It's a fascinating future to look toward.
It really is. Thank you all for joining us on this deep dive. Keep questioning, keep learning, and we will see you on the next one.